And so that is this approach where we are going to take our current mixture model and we are going to enhance it, and then that will automatically give you, using the EM algorithm, enhanced version of the soft k-means. Okay, let's look at this large and small. What is the underlying problem there? So what we had used in our mixture model is k, same with Gaussian sigma. We had said that all the sigma k's are sigma just for simplicity, right? Now we will have to remove back that simplifying assumption and then put it back in, right? So that each cluster can have its own per cluster with sigma k, okay? That will fix this idea that one of them is much larger spread than the other, okay? So here, for instance, there are these two data points which are wrongly assigned to this. We want it to be assigned to this bigger cluster, right? And this has smaller spread than this, okay? So that is one point. The other point is that we had the same prior probability for each cluster, pi 1 equal to pi 2 equal to pi k equal to 1 over k, right? I don't want that because different clusters could have different number of data points that are closer to their center. So I want a per cluster prior pi k which is different from 1 over k. It's not that a priori every cluster is equally likely. I want to also remove that simplifying assumption, okay? So essentially removing two simplifying assumptions that we put in, and then if you remove those assumptions, then we will be able to handle this particular large and small data sets better, okay? So let's just see how to do that. So let's just look at this. So the soft k-means version 2, how do you adapt it to different cluster widths and cluster proportions? If you do the E step and M step, right, we have to calculate now the responsibility vectors. We don't have the simplifying assumptions that pi k and pi k prime are all the same, so that will remain. Sigma k is also different from sigma k prime, so that will also, this term will also remain there, okay? And then you have your e to the power minus 1 over sigma k squared here in the denominator, sum over k prime 1 over sigma k prime squared, right? The distance term remains the same, okay? So what was initially only this e to the minus beta into this distance divided by sum over e to the minus beta into this distance with k replaced with k prime, that has now extra terms because we need to handle this sigma k, which is this cluster specific widths, and then we need to handle pi k, which is this cluster specific prior proportions, right? So that is the change in the assignment step, the responsibility vectors. Once you know the responsibility vectors, the mean remains the same, okay? And then the changes in the update step are only to sigma k squared and pi k, okay? We bring back the pi k is going to be r of k and then sum over k prime r of k prime, right? So the total responsibility for cluster k divided by the total responsibility, and we have seen this to be equal to simply r of k divided by n, right? So that we know that the sum of total responsibility of all the clusters have to be the number of data points n, right? And the only thing is that you have to be careful with what the sample variance is. The sample variance is again the weighted sample variance, so rk of n divided by r of k, but there are I dimensions, so there is this additional I factor, and then you have this x of n minus m of k, the squared Euclidean distance, and that is essentially either written in this notation or d of x of n comma m of k, okay? So squared Euclidean distance summed across all the dimensions, all the I dimensions, okay? This, let's see how it works on the data. So here is the initial time equal to 0. So this is your initial parameters theta 0, right, that is being shown here. These are the two cluster centers, and then you have this cluster widths, right? So you have this is m of 1, this is m of 2, and this cluster width is sigma of 2 and then sigma of 1. And then your pi is first, pi 1 is set to be 1 over 2 and then pi 2 is set to be 1 over 2 initially, okay? And then you figure out all this rk of n, the responsibility vectors, according to this theta 0. Theta 0 is set in this way, right? And then you update your vector to theta 1, new set of parameters, and that is shown here in these two new, the location of these two components are now changed here, right? And then the data points are now reassigned, so this rk of n is being calculated, and then that is shown in this pluses and diamonds here, okay? So the plus means the rk of n with respect to the cluster 2 is larger, but diamond means whichever has an rk of 1 more responsibility that this cluster has, then that is shown as a diamond, okay? So now if you keep on doing these two steps again and again, you have updated your parameter here, you are going to recompute your rk of n and you are going to update your parameter again, and then you keep on doing it. You can see here that these two distributions, component distributions of this mixture model are going to adapt better and better to each of the data that they are being assigned to, right? And then you get this and this for the original set of data points that we had. Now let's also look at this big and small data set. Okay, so this is, in this particular data set, you don't have too much of a difference in terms of the cluster width in the final 9th time step. Okay, but let's also look at this big and small data set. So the top one is the original gene A, gene B data set that we had. That is also doing reasonably well. But let's look at this large and small data set. You initially start out with this, and then you will see that the clusters are getting updated, and then one of the cluster is being pulled into this right side set of points, and they are slowly getting pulled, and then once it gets pulled, then its cluster width is adapted accordingly, and then it becomes a much more concentrated set of cluster here. And then on the left one also, it started out with a certain width, and then it's going to slightly expand, and so all the data points that was initially wrongly assigned, these 2 data points and then these 2 data points, they were initially assigned to this right side cluster, but now they have a higher responsibility to this particular cluster, left side cluster. Okay, so that fixes the large and small issue that we were having before. Okay. In order to fix the narrow and large, right, so the narrow vertical clusters, right, this lozenges data set, we are going to try a final enhancement, and that final enhancement is going to change our spherical Gaussians to ellipsoidal axis aligned Gaussians. Okay. And what do I mean by that? So initially we assume that all the sigmas across all these components of the mixture model or clusters were the same, and then we said that no, let's just have these cluster specific widths and cluster specific prior probabilities, right? But now we are going to say that, but then we were assuming that across all the I dimensions this sigma of k was the same. So if you look at the previous diagram, all of these were circles, but only the radius was different. So because each of these radiuses were sigma of k, right? But what if I want to change the radius, right? So instead of having a circle where both this and this are both sigma of k, I want to allow ellipsoidal Gaussians where this may be sigma of k1 along the first dimension, and then this is longer than the first dimension, and this is sigma k with respect to 2. Okay. So it's not only that each cluster has its own cluster width, but also each dimensions, right, each of the I dimensions also get their own cluster width. Okay. Also get their own width, let me say it that way. Okay. So if you have this sigma k of I, where I ranges from 1 to capital I, the dimensions, and then the k will range from 1 to capital K, which is the total number of clusters. Okay, each cluster and each dimension gets its own width. So now how will the 2 steps change? The assignment step, calculating the responsibility vector, and the update step. Okay, calculating the next best version of the parameters. Okay, so that one is essentially the same probability calculation. You still have to do P of z n equal to k, right, given your x equal to x of n, and then all of your parameters now theta. Now there is a more number of parameters now, right. This is still the same Rk of n. So how will this change? This will just simply become this, right. So you have your simplified formula now that you have to now deal with every dimension separately, because you have this per dimensionality cluster width. So now instead of 1 over sigma root 2 pi all raised to the power I, right. So initially you had something like 1 over sigma root 2 pi, right, sigma k root 2 pi whole raised to the power I. This was in the previous version, in version 2. Now we are in version 3. So then this has to be changed into pi I equal to 1 to I, 1 over sigma I k root of 2 pi, right. And similarly in this exponent we initially had the simplified distance one, squared Euclidean distance, where every dimensionality was treated in the same way. But now we are looking at the distance where every dimensionality have to be treated differently. We are no longer interested in spherical Gaussians, we are interested in ellipsoidal Gaussians, right, where each dimension have to be having different widths. So then we can't use the squared Euclidean distance, we need to use some distance that looks like this, right, where each of the dimensions somehow I equal to 1 to I you go, and then you look at the difference between mi of k, the center of the center k and the data point n, but only along the ith dimension, right. You square it up and then you scale it according to that dimensionalities and that cluster's width. Okay. this distance is now, previously it was the Euclidean distance or squared Euclidean distance, right, in version 3, or sorry, version 2, but now we are in version 3, and then this kind of distance is called a Mahalanobis distance. We won't get into it in detail, but just wanted to say that this is also some form of a squared distance measure. Okay. And then the denominator is going to be exactly the same as the numerator, but with sum over k prime and then k replaced with k prime. Okay. So, the beauty of this successive improvements to the k-means or enhancements to the k-means algorithm to derive new variants is that everything else remains the same. Okay. Only two things need to change. One is this responsibility vector that we have already seen, and other is this sigma I squared of k, right. So, this I and k, right. So, this kind of per cluster per dimensionality width. So, previously we had only estimates for sigma squared of k, but now we need to have estimates for sigma squared of k along the ith dimension, and that one is just simply again the sample variance along that dimension. So, you just look at the dimension I and then you look at this deviation xi of n minus mi of k whole square, that is the square deviation. Then you just do a weighted average of those, where the weights are given by the responsibility vector Rk of n that is being calculated here, divided by R of k, where R of k is the total responsibility. It is exactly same as before, sum over n Rk of n, right. That is the total responsibility for cluster k across all the data points. So, if you only change these two alone, right, then you will get from version 2 you will get version 3. Okay. Now, if you apply that to your narrow lozenges data set, right. So, how will it look like? So, this is your lozenges data set, this narrow and long data set, right. You start with this initial value t equal to 0 with these two ellipses, right, and you calculate your Rk of n for all the data points. You use it to update your theta t to theta t plus 1 using your update step. Right, those two steps are done, and then you will get this kind of changes in the two components of the mixture model that are explaining this data points. Then that is showing after 10 iterations, another 10 iterations, you can see that they are becoming, one of them is becoming narrow, another is still becoming a bit broad because it's trying to cover data points from both of these components or both of these clusters. But another 10 more iterations, each one of them nicely aligned with that particular data set or cluster alone, right. And then if you start being responsible for only this left or these right data points, then you become ellipsoidal, right. So, you are for both of these clusters, right. So, this is your sigma 1, the first cluster, this is your sigma 2. Right, and then the sigma 1 is going to be these two values, one along this x axis that is very small and one along the y axis that is very large, right. So, this is going to have sigma 1 1 and sigma 1 2 1 2, and the sigma 1 is very small and this is large. So, you get this ellipsoidal thing. So, this is I equal to 1 and then this part is I equal to 2, right. And this similarly will have two values, right. So, maybe some value like maybe 0.5 comma 10, right. So, 0.5 is this width, right, and then 10 may be this width. Okay. So, that is how this has worked. So, the lozenges data set pitfall is also handled. Now, we can also see whether this algorithm, this version 3 algorithm will work on the large and small data set also. You can see that it starts out being ellipsoidal and then it kind of like pulls together because it's trying to cover data from both of these clusters, but then eventually slowly after another 10 more iterations, another 6 more iterations, and finally at iteration number 32, this is kind of more a better fit for this cluster is an ellipsoidal fit, so that you can see here, and this one is a small cluster with that is more of a spherical fit. Okay. So, that is how it works on this particular data set on 32 iterations. So in both of these cases, you can see here that the ellipsoid's axes are aligned with the x and y axis, right. So this just essentially comes from the assumption that the different dimensions are all independent in this multivariate Gaussian that we are looking at. But in general, the multivariate Gaussian, the different dimensions need not be independent, okay. So you can even think about a version 4, it's kind of the most general k-means algorithm. What if the data is not axis aligned, that is the different dimensions are not independent of each other, right. Then also you can actually come up with a maximum likelihood estimate via an EM algorithm for the general Gaussian mixture model. We are not going to go into it in detail, this is an optional topic, okay. But I just wanted to mention that this is also possible. So here is an example of a single Gaussian that is fit on this model that is not axis aligned, right. So you have this 2 dimensions I equal to 2, but it is the axis or the axis of this ellipse, right. So this ellipsoidal Gaussian is not along the x and y axis. Similarly here, if you can also you fit the same data using a mixture of 2 Gaussians, and again you can see that the axes are not aligned to the x and y axis, right, the axis of these ellipses, which are the contours of the probability density function of this 2 variate Gaussian I equal to 2 here, okay. You can also look at 3 different components, all of those axes are not aligned, right, and then the overall PDF will look like this and the contours of that will look like this, okay. Each of these components separately with these mixing proportions and the combined contours look like this, and the combined 3D plot, right, B and C. B is the contour plot of C, okay, and C is the PDF of a multivariate Gaussian. So if you are aware of multivariate Gaussians, then this set of slides will be easier to follow. But like I said, for the purposes of this course, till version 3 you are required to know, but for version 4 it's just a fun thing to see how much general can the k-means of k-means algorithm gets, okay. So in this final example version 4, we are trying to do the Gaussian mixture model MLE learning, like learning the parameters of this model using the MLE approach, specifically using the EM algorithm, okay. So this is also known as the fully enhanced soft k-means algorithm, because everything we are kind of making it more general. We are having a general multivariate Gaussian for each of these components, and then we are having a general mixing of all of these, right. And so then how will the assignment step, E step and the update step look like for this generalized fully enhanced soft k-means? It will look like the following. For a multivariate Gaussian where the axes are not aligned, where the axis of the ellipse of the Gaussian's PDF is not aligned with the actual axis, where this independence assumption is not there, then you can have a general variance covariance matrix. So a multivariate Gaussian is defined by a mean vector mu k that is of vector of length I, right, and then sigma k, which is I cross I covariance matrix. So mu k is r to the I, and then sigma k is in r to the I cross I. So it's a matrix, right. When sigma k is an identity matrix or a diagonal matrix, when sigma k is a diagonal matrix, that is when we get this version 3 of the soft k-means algorithm, okay. But if it is a general positive semi-definite matrix, okay, so that is the variance covariance matrix, right. So that is the parameter for a general multivariate Gaussian. Then you get this particular version where you can see that pi k and then the normal PDF for this multivariate Gaussian, xn given mu k comma sigma k, and then sum over the numerator with k replaced with k prime, okay. So this is just a simple generalization of the formula that we have seen so far, the same calculation of the hidden cluster labels for each data point, but under this general mixture model assumption. The update step is going to be again the sample average Rk of n over Rk x of n, right. Again the sample variance now becomes a sample variance covariance matrix, okay. So this turns out to be the sample variance covariance matrix, but weighted by Rk of n over R of k, okay. And then you have pi k nu, this pi k nu turns out to be the same, R of k total responsibility for cluster k divided by n, where the total responsibility for cluster k is sum over Rk of n, okay. So how will this fully enhanced soft k-means work on this kind of a data set, right? So you may start out with this blue and the red being the 2 components of this generalized mixture model, right, general Gaussian mixture model, and then your responsibilities for each of these data points are calculated and they are being assigned in a soft way. Those that are closer to the blue blue mean over here are getting darker blue, and those that are closer to the red are kind of pure red, and those in the middle are getting this mixture between blue and red, I believe a purple color, right. And then now in the next step you are going to update the parameters. So this is the calculation of Rk of n. Now you update the parameters using the computed Rk of n using these 3 equations, right. So the first step is calculating the responsibility vectors. That is how these points are colored, and the next step is updating your parameters to the next set of parameters, and then that is being shown as these 2 ellipsoidal component multivariate Gaussians, right. So in this case there are 2 dimensions, so it's a 2-variate or a bivariate Gaussian, okay. So now you have these 2 ellipses, and then you go on and recompute your assignments. I mean this is your updations, right. So these parameters are being updated. Now you go on and recompute your responsibility vectors. So you have this colorings are now changed, and using the changed colorings, the changed responsibility vectors, you again update your parameters, and so this blue one now doesn't have to cover anything like these data points, so it can shrink along this dimension, right. And you can see here that the ellipses, these 2 ellipses, right, the axis of these ellipses are not aligned to the x and y axis, so they are allowed to be not independent, right. So the dimensionalities doesn't have to be independent of each other, so they are allowed to be dependent and correlated in this particular case. Finally, in 20 iterations you have these 2 component Gaussians fitting these 2 particular clusters, and the colorings are all mostly blue or red, but then those in between you will have shades of purple there, okay. Now compare this fully enhanced soft k-means to the hard k-means that we had before, where we strictly assign every data point to only one of the clusters, okay. So that also kind of through these different steps gets assigned these 2 clusters, but we understand less about each of these clusters. Here in the soft k-means, fully enhanced soft k-means, we also know something about the underlying data distribution of each of these clusters, that this is a multivariate Gaussian that is whose ellipsoidal axes are aligned in a certain way. So we get more information about each cluster, right, compared to this hard k-means. And also for those data points in between, it's not very apparent in the coloring here, but there are some fractional responsibilities for those that are in between these 2 data points, okay. Those fractional responsibilities are also missing from this hard k-means, okay. So that comes one full circle, and so we have seen all of these variants starting from hard version to the soft version vanilla aided by intuitive formula to a soft version vanilla aided by a connection to a probabilistic model, and then finally how we can use that connection to a probabilistic model to design new variants of this k-means algorithm, okay. So probabilistic mixture modeling as a summary and the associated statistical inference gives a very systematic approach to design and optimize this data science task, right. So it is useful to understand the probabilistic underpinnings of a particular data science task such as clustering, and then that can help us design new variants. So soft k-means is successful in many applications, example cancer subtyping, okay. Though it's still not perfect, so there are many other clustering algorithms possible. So we took this as an example of how a probabilistic thinking can help us, okay. And like pushing this along, so the maximum likelihood estimation blows up when the mean sits on exactly one data point. Then what is the variance of that, right? Well, the variance will then go down to 0, right? In those cases, there is this concept of Bayesian inference that will help, but those are in the end, I want to summarize by saying that this clustering, a very popular data science task, can benefit from a probabilistic lens to view this clustering task so that we can design new variants. And this doesn't stop here with maximum likelihood estimation. There are other ways using Bayesian inference to also make this whole process more robust. Okay. Thank you for your attention and patience listening to this set of ideas on k-means clustering that is mostly based on the book by David McKay. Okay. Thank you.